Now, I do have to say that us sitting here indoors on such a lovely day is quite a testament to how much we apparently love Clojure. I'm Simon, and today I'm going to talk about our experience using Onyx. So kind of to get started, how many of you have heard about Onyx? Most of you, good. How many of you have used it or just kind of toyed with it or something? Couple. Okay, so I have a lot of room to work here. Okay, so basically a quick recap. Onyx is a masterless, cloud-scale, fault-tolerant, high-performance distributed computation system written in Clojure. You can think of it essentially as it operates the same area in the same space as something like Apache Spark or Storm or something, but comes with a couple of different twists, which I'm kind of going to talk about. Now, in terms of our experience, we're kind of using it in almost kind of any imaginable capacity. So we've been using it now for about a year, and we're using it to do our ETL. We're using it to essentially run our online machine learning. We use it to train our offline or batch machine learning models, and we also sometimes use it for ad hoc analysis, kind of just doing exploratory data science in the cases where you have so much data that you just can't do it on a single machine. This is we're just kind of a pretty small startup. So one thing that's quite important for us is that the systems we put in place are as kind of self-service as possible, because we don't have a huge DevOps team, and I think even if your organization has it, it still presents additional friction in terms how the data science team can do its job if you're going to have to pay a lot of heed to just your infrastructure. So one thing I'm very picky about is to kind of figure out what kind of infrastructure can we put in place that you can do your tasks with data as quickly as possible and with as least friction as possible. And this also kind of has a lot of ramifications in terms of how effective your data science department is if they can do their job quickly rather than having to kind of schedule, bring all different people together to make some analysis or something like that. So kind of this is something that kind of heavily has influenced my thinking, and also which kind of what goes in hand with this is the power of having a live environment. Now, we're obviously kind of used to this by using REPL, but as soon as you kind of move away from just being in a purely Clojure ecosystems, as soon as you start to use other systems, the niceties of live programming quite often kind of go through the window. So this is also something that I found is quite important just in terms of how quickly can you arrive at a solution that you have an actual kind of live environment with all things you do. So, and Onyx here, I do have to say, has been a big step forward for us in those cases where you do have to have some more infrastructure rather than just kind of running your Clojure directly. So this talk essentially is going to be in three parts. First, we're going to look at Onyx as a glance, so sort of maybe a recap, since most of you know it, but just what are the main things. And here really this talk is in no way an attempt to kind of show you how to actually use Onyx. It's not going to be a tutorial, but rather I'm going to focus on how Onyx changed the way I approach certain problems. So just kind of this Onyx at a glance is just going to be some of the highlights and why I think those are important. Then I'm going to talk about how Onyx essentially rewired my brain, so more of this, how I'm approaching some problems differently, how I'm thinking about some problems differently, how my architecture choices have changed in a lot of ways, also kind of as a response to adopting Onyx more and more. And last but not least, I'm going to talk about essentially putting the data is code paradigm to work and what kind of things we can build with that. And this is probably, this last piece is something that's going to combine a recurring theme throughout this entire talk, which is talking and thinking about how we can describe our computation and also our data with data, and how this is a very powerful way of going on about things. So let's get cracking. Brief tour of Onyx. The main worker unit in Onyx is called a job, and it's comprised of three components: the workflow, flow conditions, and catalog. So the workflow is essentially your computational graph, so how the data moves through your system. So it comes from input and then sent to one process, another, and so forth. Maybe you do some fan-outs, fan-ins, and things like that. Then the second part are the flow conditions. These kind of act on your flow graph and can essentially limit how the data flows based on some conditions. And it also enables you to do error handling. And here you'll notice that this is already kind of one of the, I think, the more beautiful design decisions in Onyx is that we're kind of decoupling those two things. So we have a kind of a very abstract or general representation of your data flow in terms of our workflow. And then we all the gritty bits with error conditions and various conditional flows and so forth come in as separate components. So you don't have to mesh all those together. And I find this is a great thing also just about thinking about this, or how quick it is for someone who is new to a certain code base, to a certain workflow, to figure out what's going on. Because you can just first start with a workflow, which will give you this kind of rough abstract idea of what's going on in this computation, and then you can dig deeper into the various details in terms of, okay, when do we actually flow data around and so forth. And the last part is the catalog, where essentially you define all the units that we've talked here, so all the elements of our workflow or flow conditions and so forth. Now then there's also a bunch of other things you can stuff into a catalog, but as I said, this is no attempt at a tutorial. Onyx has a lovely getting started guide, which I do invite you all to read. I think it's one of bare examples of very clear, although very technical writing, so do give it a look. But this is just sort of as a give you a rough idea of what I'm talking about when I'm talking about describing computations with data. And just, again, this is kind of the same story. If you look deeper into the catalog, you see that we have kind of different entities for functions or various inputs and outputs. And here the nice thing is that any kind of function that actually performs some task is just a vanilla Clojure function with essentially the entire protocol being this convention that the data are going to get in, called segment in Onyx vocabulary, is essentially a map, and that's it. And this is kind of enough. This is all the ceremony you need, and then you can just plug in any kind of Clojure function. And one thing that kind of turns out can be quite useful is that you can also specify some of the parameters. So essentially, you can make a curried function already within your catalog. And why this is kind of useful is for things like if you're doing, we're using this a lot in machine learning applications where you can use this to, we have different sets of hyperparameters. And you can this is a very nice way of doing things, and it can have several different versions if you're searching for the best hyperparameters or wanting some benchmark or something like that. Again, reinforcing this notion that we're decoupling different things, and you don't have to worry about where to inject different starting settings or something like that. And also, this parameters can be, in this case here, it's statically defined, but it can also be decided on the fly with what Onyx calls a life cycle. So you do have also an option to inject your computations at various stages as your data flows through, and this gives you another meta layer of how you can adopt your actual computational workflow to the specifics of what's being worked on right now. Then in terms of I/O, you basically get all the connectors that you would expect. Kafka, Datomic, various SQL databases, Amazon S3, SQS, and so forth and so on. And you also get an option of using local data sources in terms of either normal Clojure sequences or async channels. And this is also something that turns out to be quite useful in two ways. One is that it eases testing, and I'm going to come back to that later. And it also sometimes you can just use Onyx essentially just to orchestrate your computation, even if you're just doing everything locally. And all the parts also do carry nice documentation. So not only is the system self-describing in terms of data, but you can also describe it in a human-readable sense, which again is then very simple to just automatically pull out different bits of documentation. And again, as you're confronted with a new system, you can just interact with it at the REPL and look at all the various doc strings and then slowly understand what's going on there. Right. So so as I said here, Onyx essentially, all the kind of everything that there is to it is basically are just normal Clojure data structures, which you can manipulate in any way that you normally would. And as luck would have it, also Clojure is rather good at manipulating such data structures, so it's kind of very easy to build various meta layers on top of it. Now, on the one hand, this is something we're already kind of used to by being Lisp programmers in terms of doing code macros. But it turns out that like once you want to write slightly more complex macros, it can get kind of pretty nasty to just kind of handle all the specifics of the syntax, while sort of a more, let's call it unrolled syntax like you have here, which is just a direct data structure, is very, very convenient to manipulate. So I would say that kind of here the balance changes. If normally we have this kind of a rule in Clojure that the first rule of using macro is don't, I would say that as you kind of moved from kind of describing your computation in code to describing it in data, this kind of notion changes because there's just like, there is less kind of magic to it, it's easier to inspect, and also just like it's massively easier to work with. So kind of what are all the kind of the benefits that we get from all this kind of from the Onyx's design? The first one is that everything can be run locally. And even actually with the latest couple latest versions, even in Clojure script. And that gives you immense power in multiple ways. One is that it opens up new venues for tooling. And here the team behind Onyx just recently released or showed a demo of something they called Pyroclast, which is essentially kind of an online visualization and debugging tool for your Onyx, which what it does is that it's kind of in real time in your browser visualizes how data flows through your Onyx system. And it's a fascinating bit of software and shows you what kind of potential this has, that it's just data structure. So it's kind of very easy for us to build kind of tools on top of it. Second of all is that it's kind of, Onyx is very self-contained, almost to the point that you could consider it to be a library. There is some, like if you want to run it just locally, there is some minimal setup involved, but it's essentially as easy to run locally as something like the Atomic or something. So kind of you don't need to go through all the hassle of having a zookeeper and so forth, but can be run locally. And everything, again, can therefore also be kind of inspected as you would expect in your own REPL, which is a huge, huge win. And this also gives, I think I would dare say that it also makes it a much more gentle learning curve, that essentially everything can be done locally, because you don't have this kind of threatening first step for, yes, now take this Docker container, set it up, and then you need the zookeeper, blah, blah, blah. And like many of these kind of distributed computation systems just have a very high barrier to entry before you can even do the hello world example or something like that. While here, it's essentially is just a Clojure library. And this is kind of, yes, if you're kind of deciding on a company-wide level of which technology to use, this is not a big argument, probably. But it does make immense difference if you kind of use it in a more ad hoc context. And this is, I think, like what makes me so excited about Onyx is exactly that it changes the paradigm of having stream computations as being something that's kind of relegated mostly to sort of a infrastructural solution. Rather, now it just moves the needle to essentially Onyx being a way to just to solve your problems. It's not just a question of scale, but it's more becomes a question of organizing your code. And kind of it turns out that, or rather at least I think it organizes in a way that kind of is rather lovely to work with. And I already kind of said, you also can have just use local sources and so forth. So essentially, if you have a kind of a slightly more involved computation, it sometimes even kind of makes sense to just maybe have Onyx kind of do it in a completely local setting. Sometimes it's still kind of overhead, because if you remember, like looking in the catalog, it is slightly more verbose than just writing directly Clojure functions. But where it does kind of shine is if you have kind of more complex flow, how different kind of function and data flows from one to another, that kind of makes more and more sense to decouple this. Kind of hand in hand with this, it also means that you can do most testing without mocking, because again, it can run locally, and because you can just plug in different data sources, and if you're using something like Spec for your data, then it's very easy to essentially kind of test very lightweight, but also kind of very close to what's going to be actually happening in production. So imagine your data is described with Spec, which means that we can just kind of exercise it and generate different examples of this data. And if we connect this to some async channel or even just a sequence, we can get essentially kind of any chunk of our system that we want to test without kind of going through the hassle of setting up all the bits and pieces that comprise of our entire system, but have this kind of just locally and tested there. And again, that's a huge win, and just kind of, again, lowers the barrier to entry in terms of how hard it is to develop such systems, and kind of and we can just apply essentially the same development principles that we've kind of normally used to. Okay, so these were kind of the highlights of what Onyx brings to the table. So how did this kind of manifest in day-to-day work? First of all, and I already kind of hinted at this, is that it's not about scaling anymore, but it's about a clear architecture. And that, I think, is like probably the biggest indicator of how good Onyx is, that it opens a new way of how we can structure our problems. So you start with a tool that's an answer to kind of a very concrete problem of, okay, how can I do stream computation on a larger scale? It does it so well that, in fact, it also kind of introduces a completely new way of solving problems, because it abstracts enough things in a way that it's going to make sense in multiple contexts. So again, it does depend when does this make sense. I'm also kind of, something that I'm tempted to do but haven't gotten around to it is to write kind of some essentially a DSL over Onyx that would simplify just running in a local context where maybe you don't need kind of all the ceremony, so that essentially you wouldn't even have to pay this much of a price. But even now, as I said, we are already kind of sometimes using it for more complex data flows, even where scale is not an issue, but just is something that's is supposed to run locally. Now, in terms of architecture, and this is kind of pretty right by now, I think it's sort of general. So if you give me some new task where I need to build a data layer, how I would almost certainly start is something like this. So essentially, kind of all the data coming into the system gets written to Kafka, and it's also persisted to all the messages coming in, also then persisted to S3. This gives us two great advantages. One is that it allows us essentially kind of to time travel. So at you can always replay history from your S3, and this is great for two reasons. First of all, if you make some mistake with your processing, you aren't losing data, and second of all, then this allows the system to grow much more naturally, because you don't have to think about all the usages for your data up front, but you can just kind of extract the minimum that you need right now and still be safe in knowing that you aren't actually losing any data. Right, so and then here's where Onyx kind of comes to its own. Onyx reads off Kafka and then kind of does various things with this data, usually stores it into kind of several different databases or one or whatever, and sometimes also kind of generates new events, so you have this kind of cycle here which repeats itself. So, and kind of, I'm a big fan of kind of very aggressively decoupling reads and writes. Now, obviously, kind of this entire architecture does this, but also like if you look at here at this point in the database, what I prefer is to kind of have separate processes, one that just writes something to the database, and the second one that responds to what's happened, rather than coupling those together, because again, it's easier, first of all, to just isolate some functionality in terms of testing, understanding what's going on, and I also just find that it's cleaner and kind of more robust. And kind of continuing this topic, it's basically what the Onyx gives you is further tools to kind of to decomplex more things. Now, if you couple it with something like Spec, which I find it goes very well with Onyx, you essentially we're using Spec, so we're kind of decomplecting validation, and our functions just kind of get magically validated as they're run. And then you don't have to handle those kind of exceptions within just your code flow, but this is something that's done separately with the flow conditions of Onyx. So again, we have another concern that we don't have to think about, and the same goes for logging and so forth. So what happens is that you then end up with a very pared down code which actually just solves the core problem that you're having, and everything else kind of is then stored in different layers and solved there. And this is something that, again, greatly helps in just understanding what's going on. I don't know about you, but kind of I find that I can essentially hold about 200 lines of Clojure code in my head. And it's kind of a limit. So I find that it does make sense to kind of try to code against this my mental limit and make sure that what I'm actually working at, the complex problem that I'm solving, that can be so compact. So it makes a lot of sense to try to kind of remove all the external bits that don't really kind of influence what's going on in terms of solving the problem, but are rather just some part of the plumbing needed to get there or to have this work in a production setting. And obviously, this is not some radical new idea. If you look at most of the kind of machine learning frameworks nowadays, they all kind of tend to describe the computation going on as some form of graph. And so I think this is kind of a very nice step, but still right now it's usually tied with some notion of having some very complex, very big computation. What I kind of propose here and invite you to do is to think about kind of how most of computation can first of all be thought of as a graph and also kind of explicitly coded like that. And it turns out that kind of oftentimes it does simplify things greatly. And this is like sort of an analog from if you're doing a lot of kind of data processing, you're probably also using a lot of either the threading macros in Clojure or maybe transducers if you are kind of more enlightened. But kind of in both of those cases, like they work rather nicely when you have just a linear flow of data. But the moment you want to kind of split this around, it breaks down. And kind of this makes me sad because like I'm a big user of threading and it just makes code very nice and very readable. And what graphs gives you is essentially a way to model even kind of the more complex workflows with the same elegance as you would have with threading. So do start kind of thinking about how this is just essentially like how my computation is a graph and then what I can do with it. So, and now for the last part, putting all this kind of together and I hope that I've already kind of outlined some of the differences in terms of what you gain just in your day-to-day life and how your life is easier as a developer by adopting this approach. But there are also kind of some things you can build on top of that that also kind of tend to be quite nice. So now here just a short interlude because Spec is going to kind of feature quite centrally in this example as doing something like what kind of query the data descriptions with Spec. So the idea is that essentially, if you are kind of good in defining most of your data with Spec, all this kind of then is stored in your registry. And you can then get specific definitions out of it with a Spec form. It's kind of the back. So what essentially we then can do is we can walk around this registry and start to do something with it. For instance, we can build a graph of all of our specs and then can look at how things can combine together. Because this is kind of one of the nice things about Spec is that it forces you to think of kind of a very small fundamental element and then kind of build those up. At the beginning, probably you might thought that it's kind of annoying that you have to define each key for a map separately, but it then turns out that this has some very nice properties in terms of that it does force you to kind of reduce things. And it sometimes kind of it makes sense that you maybe want to understand how things connect together. So if you if you parse this, and because Spec is very nicely parsable, thanks to being just a regular expression, it's quite easy to then say, okay, these are kind of some rudimentary relations like this spec always contains this element, or this spec may contain this element, and so forth. And if you store this in a datomic, you can then also query it in different ways. And what we now have is essentially kind of our own type system, at least over the data we care about, with which we can fully interact. And this is one of the things where also I think that Spec is brilliant, is that it finally, I think, cracked the question of how does a type system look like in a fully dynamic language? And I think this is Spec is a good, at least first step towards a conclusive answer to this, in terms of that it is a system that is fully interactable, that you can interact with it as your code is running, rather than just being something that's essentially a service of your compiler. Right, so now imagine that we do have some kind of a graph representation of something of world data types. Now, what we can do is then something like this, and this is what we're actually using in production. The idea is that we want to generate many materialized views automatically. Now, materialized views are kind of a nice thing if you are working with data, because they do either they kind of serve couple of functions. First of all is that it makes sure that people kind of tend to use the same starting point when it comes to data, which does remove one class of errors or bugs. The other one is that it oftentimes allows you that you can do more on your local machine rather than having to do some kind of massive computation, because you can already have data pre-aggregated in some way that's useful. And it also just kind of removes the most often repeated parts of your coding where you just kind of pull data together. But at the same time, they also have some problems. One of them is that oftentimes you'll have almost the exactly correct materialized view, but not quite, and then you're back to square one having to use raw data. The other one is that they are kind of brittle, and that you often spend enormous amount of time just kind of maintaining all this and making sure that it's done correctly and so forth. So it would be nice if we could do this somehow automatically. And it turns out you can get quite far with not a lot of complications. So the idea is that we describe all the data coming into our system with Spec, and then we have a predefined ontology of event data and some attributes, which kind of helps us to ground this into what's happening in terms of our domain, to kind of imbue some domain understanding to what the data is. And then we also have a bunch of heuristics of what to do. So for instance, things like if you find user field, then it makes sense maybe to have some version of this data where this is enriched with some of the aggregate statistics about this user and so forth. And we also kind of do some very rudimentary statistical analysis to look at things like, is there some seasonality? And if so, it probably makes sense to do kind of those specific aggregations up front and maybe some outlier removal and things like that. So kind of more conceptually, what's going on here is that we walk the spec registry, and then we just we start applying those heuristics. So we apply the various kind of the ontology that we have and statistical rules and so forth. And we see if we can define a new spec. And if that happens, then kind of this in turn triggers the appropriate processes to actually build those materialized views. So what we do is that just like using essentially the kind of domain information or the semantic layer about our data and the concrete instance of what the data is, as described by Spec, and use that to essentially pull together an Onyx job on the fly, which then takes this data and saves it into a materialized view. And then kind of the cycle is repeated, because maybe this will then trigger some other heuristic and so forth. So it can kind of, you don't have to even do all of them kind of upfront, but it kind of slowly one triggers the other one and so forth. And this kind of system then just runs and adds new things. We're now kind of at the point where there are slightly too many of this kind of views, so we also have some cleanup mechanism which looks at usage statistics, and if something is produced that's never used, we then just remove it. But essentially kind of this is a way where you can have a very small team which spends very little time in kind of this housekeeping mode and still have a top-notch data warehouse. And this kind of also brings me to this kind of maybe a philosophical point, because there is a certain, like when you're using Onyx and Spec together, there is this certain ideological clash in a way, in the sense that when we write code equals data, but it's not quite equality, because like one is favored or the other. So what makes more sense? Kind of code first, and then treating code as data, or data first and treating data as code. Like Spec is a clear example of code is data, and this is also something that Cognitech is upfront. If you look at the design brief behind Spec, they say that yes, we've intentionally decided to optimize Spec for human readability rather than for machine readability, because we think that this is how it's mostly going to be used. While, for instance, Onyx goes more the other way, with this kind of data-first approach, which may be not as nice for us humans to write, but it's kind of massively simpler when it comes to parsing. And I do have to say that there's quite a big difference, even though kind of Spec does help that there is kind of this parsing of derivatives concept behind it. So it is quite nicely parsable, but still I would take an Onyx data structure any day of the week in terms of how easy it is to manipulate. So like there is no obviously kind of clear-cut answer, but it is sort of an interesting twist to this often repeat mantra of code is data. And though I think that probably the optimal kind of trade-off is to allow kind of, at least to a certain extent, both. And this is, if you think about it, this is exactly what Datomic does. Because in Datomic, if you look at the query syntax, like mostly you would use the vector one, but they also kind of support the second one, which is a map where you have different parts like the where and the in and so forth are kind of separated out. And this is, and also internally, what happens is that Datomic will transform the vector representation to the map representation because it's much easier and nicer to kind of to change it and manipulate it. So I would like, my hope is that eventually, like more and more systems are going to adopt this duality quite upfront. That yes, we have some affordances for users to write this, but also allow kind of the full power of it for our machines. So, in conclusions, like what are the main things I would like you to take out of this talk? The first one is kind of maybe self-explanatory, but I do think it does kind of warrant emphasizing. Onyx is production ready. Now we've used it for a year, didn't have any issues. Speed, at least for our use cases, seems to be on par with Spark, so kind of highly recommended. And I hope that the next time some speaker is going to ask you who's using Onyx, we'll see more hands up. The second is that everything kind of should be live and interactive. And this also means things like we've seen some attempts at this conference already in terms of not just your code and your code environment, but also kind of your wider environment, your infrastructure and so forth. And again, Onyx is a good step towards that in terms of doing string computation. Then just the computation graphs are a great way to structure your data processing code and kind of should be used more and should kind of become more first-class citizens in kind of many data-centric operations. And the last but not least is that queryable data and computation descriptions are, first of all, a great asset when it comes to just having a really truly interactive development environment, or a building block for that, and they also allow you to build some very nice automation with very little effort on top of it. And again, I think they kind of go back to this original kind of Lisp notion where we have just a continuum from your code on one, your problem-solving code on one end, and just a continuum towards your tools, and kind of describing your infrastructure in this way kind of brings this same magic back to something that's oftentimes kind of slightly dreaded by people using it. Oh, now I have to use a grid computation block and so forth. But if it's actually kind of, Onyx shows you that if this is done right, it can be something that actually kind of you want to adopt even in other use cases rather than something that you have to be wary of. And with this, I kind of yield the floor to you if you have any questions, or if you want to kind of just track me down later. I'd love to talk about this for ages, so have a go.
So, any questions? Yeah. Somebody said yeah, but... Oh, okay.
So I wonder, how is fault tolerance implemented in Onyx? You said like scaling is not a problem, but fault tolerance is the key for scaling, right? So can you give me a hint?
Yeah, like one thing I maybe haven't emphasized enough, like we don't have super massive data sets, so maybe like it's a good chance that there are probably continuing issues if you're on the edge of what a processing kind of framework can handle. But I think that like it's the same as with that joke that if you look at the biggest instance on Amazon, how much RAM it has, if you have your data is less than that, you aren't big data. So kind of I think that a lot of us aren't kind of that aren't pushing the envelope that much. But in terms of like, we didn't kind of have much issues. I think it's also kind of, oftentimes it's just also a question of how you do your kind of entire infrastructure. That if you're kind of very diligent with splitting your reads from your writes and things, decoupling those things, and just kind of think about that, you kind of automatically gain a lot of fault tolerance. And in terms of how it's implemented in Onyx, they do have a couple of different strategies which you can control, which is, again, it's kind of nice that you aren't kind of set into one way, but you can configure it. And again, all this is something that you can also interact with and inspect in a running environment. So it also kind of think that it's even possible to change it on the fly, although this is something that kind of we haven't done because just there simply wasn't a need. So yeah, like, to be honest, we haven't really kind of touched this because there was no need, but I think this is also kind of a testament to how well it's done. That if I can kind of compare previously when we were using Spark, we had, even though we had much less data, we had to spend much more time in just kind of managing Spark and making sure that it's happy and all those things, while with Onyx, it just seems to work. Now, some of it, again, might be that technology as a general kind of is progressing, and now that also Spark is kind of better those things, that's a fair point, and obviously also kind of Onyx does use some other components which might also kind of mature in this time, but we didn't really kind of have any big issues with it.
Okay, but if your long-running streaming job fails, can the system automatically recover?
Yes. Like you mean if what kind of failure mode are we talking about?
Yeah, for example, you taking streaming data from customers, maybe a click stream.
Yep.
And you do some aggregation on some window and then write to database, for example. If it fails, will it produce wrong result? For example, wrong number of your aggregated results. So this kind of tolerance is guaranteed by frameworks like Spark or Flink. So if you have some mechanism in Onyx to make sure the number is always correct, even though there might be a few failure, over the period of the running.
Yeah, I think the biggest limitations are in terms of how new job running nodes can pop up and disappear if you're using some of the current degrouping things, because they do, if the departitioning they're using doesn't hold through. But even that is kind of, you can control how this happens, and sorry. The general approach is going to be to just kind of restart and retry where it happens, but I think with some grouping operations, it is limited that if some node goes down, then it can't kind of be rejoined as the job is running. Now, it's not going to compromise the running of it, but you can't add more nodes. So if a node falls, the workload is going to be spread across the existing ones. Now, kind of if all going to start to die off, and you have so little that you can't feasibly finish this, then I think you would have an issue.
Okay.
This is kind of my understanding.
Okay, thanks.
You have 2 questions here, right? Oh, okay.
Hi, thanks. You said everything should be live and interactive, but then in the graph, in your pipeline, you're using Kafka. So do you also need the Kafka locally to try things, or what is Kafka used for in that pipeline?
No, like for most of development, what kind of we're using the approach kind of I outlined, that instead of reading from Kafka stream, we're just kind of reading from some local async channel, which kind of producing the same data, and from the perspective of testing your computations, it's obviously the same because it's the same data going in. And here again, as I said, we're heavily leveraging Spec to kind of just generate test data. So for the most part, we just test this, and also I do have to say that now thinking more, the more we're using the entire combination, I could also, an argument could be made that Kafka in this instance is actually an overkill, that you could use something kind of much simpler, like for instance, just writing directly to S3 and then using the notifications from S3 to just fill up a simple SQS on Amazon and then use the Onyx to read from that. So this is, if you kind of don't mind to be tied more tightly to the Amazon ecosystem, that looks like a very nice way of doing it. So yeah, essentially, probably Kafka in a way is kind of a leftover from previously, and just and they are kind of also seem both to move into the same space. Now with Kafka, recently they've introduced the Kafka streams and so forth, so they are kind of moving more into the also processing direction, so there is kind of more and more overlap. So yeah, it's a question if it makes sense to even kind of keep Kafka there.
Thanks.
Any other questions? Yeah.
And what about the performance compared to Spark, for example? Are there some benchmarks? How did you look at it?
There, I seem to remember. Actually, I wanted to look this up for this talk, but I couldn't find the blog post I had in mind. So this is kind of going to be anecdotal, but at least for our use cases, they seem to be on par. Okay. So there, we haven't had any performance-based issues with it. Maybe it might be that many of the things we're doing are probably computation is dominating I/O. So maybe if you have something that's kind of very strongly I/O, then I don't kind of want to say that this is also kind of equivalent. But if you are more kind of erring on the processing having side, then definitely kind of on par.
Okay, that's pretty much it, I think.